Hello everyone, my name is Jonathan Coria and I am a third year biochemistry student here at UTA. I'm currently doing research with Dr. Peter Kroll, where our research is focused on the self-diffusion of nitrogen in 3D silicon nitride. When I say diffusion of silicon nitride, I'm referring to the collective process that all atoms follow, in which they migrate away from their original positions over time as a result of Brownian motion, the random movement of atoms due to collisions with other atoms. We conduct this research through the use of molecular dynamics simulations using a supercomputer located at the University of Texas at Austin. These simulations take approximately 10 to 20 hours to complete, and the key property that we extract from them is the mean square displacement, or how much an atom has migrated away from its original position. This is a microscopic property that we observe, and thanks to Einstein's relation, we are able to analyze the diffusion coefficient d, which is a unique property on a macroscopic scale. Using this diffusion coefficient, we can use it within the Arrhenius equation in order to extract activation energies for the systems that we are looking at. We're conducting a comparative study where we compare 5 different potentials that determine the bond strengths between silicon and nitrogen to see the effects on both diffusion and the activation energies yielded. These potentials are the Tirsov-1 potential created by Peter Kroll, the Tirsov-2 potential created by Brito Mota, the SG potential created by Stephen Garofalini, and the MG2 or Marion and Gastrike two-body potential. The fifth potential is the ab initio potential, which is special as it is a highly accurate quantum chemical method that many would trust before exploring other potentials. However, this method is very expensive as the simulations using this potential take several months to complete. By treating the ab initio as our standard, we can then judge which potential is best based on what we are looking at. We are exploring these diffusion properties between the range of 4000 and 5000 Kelvin on the same model of silicon nitride, which is a 5 nanometer cube consisting of over 1000 atoms. Using the mean square displacement that we get from our simulations, we plot this versus evolved time in order to see lines that represent the mean square displacement of nitrogen as a function of time. On this poster, I only show the mean square displacement versus time graph for the Tirsov-1 potential as an example of what it is that we do for all the others. Each colored line corresponds to a different temperature between 4000 and 5000 Kelvin in increments of 200 Kelvin. And as we can see, we have nicely linear and ordered lines that demonstrate increasing diffusion over time. As the temperature increases, so does the diffusion. Taking the slopes of these lines for the individual temperature ranges yields values of d that we can then use in our Arrhenius fits. Now, as I said before, we do this for each of the different potentials that we use, but rather than showing you all the graphs, I opted to show the differences between each one at one temperature, this being 5000 Kelvin. As we can see, the ab initio potential has the most amount of diffusion occurring at this temperature, as seen by the very steep slope when compared to the others. In contrast, the SG potential shows almost no diffusion at this temperature, essentially being frozen. Remember, the different potentials determine the bond strengths between silicon and nitrogen, so this is one way to see the differences between each. By extracting the diffusion coefficients between 4000 and 5000 Kelvin for each of these potentials, and plotting the slopes as the natural log of d versus inverse temperature, we are able to extract the activation energy, since this is essentially an application of the linear Arrhenius equation. Once again, I showed the graph only for the Tirsov-1 potential as an example of what we do. Each of the points on this graph represents the diffusion coefficients or slopes from the previous graph for each temperature explored. The slope of the resulting line is equal to the negative activation energy divided by R, the ideal gas constant. So by multiplying the slope by -1 times R, we can then get our activation energy. Those that have results most closely to that of the ab initio potential are theoretically to be most trusted, and in this case, it would be the MG2 potential, as it is the only one that is best able to replicate data of the ab initio as seen by the intersection between the two in the graph, where all the potentials are being compared. However, if we were interested in the mechanisms of the atoms, then the Tirsov-2 potential would be best, as it yields the most similar activation energy of the ab initio. This is only true for the temperature range between 4000 and 5000 Kelvin though. If we were to go to lower temperatures like 2000 Kelvin, then it's likely that the Tirsov-1 potential would be best, since looking at the comparison graph, it seems the two would intersect at lower temperatures. However, this is simply a bold assumption, since it is not taking into account that these systems may not be melted at lower temperatures than the ones we see here. Now, some of you may ask, if the ab initio is the best, then why do we not always use that potential? To which I would respond, again, it's the most expensive method, and it takes months to complete or produce data, while that seen by other potentials only takes several hours in comparison. What I've essentially done is compare different potentials that researchers use to see what they can expect or what they can rely on. One direction we may explore this research in the future is study the effects on the diffusion of silicon nitride when found in complex nano-carbon systems, but that's a story for another day. I would like to end by thanking UTA's undergraduate research opportunity program as well as the NSF PIRE program for funding this research. I would also like to thank the TAC Center for allowing us to run our simulations on their supercomputers.